All right, my Calculus 1 friends, we find ourselves in Chapter 3, Section 9, which is the last section of the differentiation rules chapter. And in this section, we're going to talk about related rates. And I think I can safely say that this is going to be the easiest section of the entire chapter. Let me show you what it involves. Related rates is very much as it sounds. We're going to work with some very specific equations that will help us relate the rate of change of one measurement to the rate of change of another measurement. For example, in this analogy / example, we're pumping air into a balloon, and as the air goes into the balloon, both the volume and the radius of the balloon are increasing. However, their rates of increase are different, but they're related to each other. And so that is the idea of related rates. And it involves the chain rule, and it involves the chain rule by way of implicit differentiation. And I'm going to show you what I mean in this one example, and then I'm going to toggle over and look at a couple of homework problems. Just make sure that you have all the equations that you need in order to work through those, and you'll be on your way. So in this example, air is being pumped into a spherical balloon so that its volume is increasing at a rate of, so they're giving us dV dt, the rate of change of volume with respect to time, 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is? So this is sort of marking a particular point in time by way of giving us a specific diameter. Now, it'll be part of the process, but the equation for the volume of a sphere is 4/3 pi r cubed. So they're giving us a diameter. They think they're being tricky here. We're going to have to take the diameter, cut it in half, and turn it into a radius. And so the recommended process is that we identify a couple of things first. One is the given information, and we already talked about that, and the other is the unknown. So what we're trying to find is the rate of increase of the radius when the diameter equals 50. We don't want to know the radius when the diameter equals 50. We want to know the rate of increase of the radius. That's going to be dr dt, the change in radius with respect to time. In order to do this, we're going to need an equation that involves volume for a sphere expressed hopefully in terms of its radius. And my recommendation in all of these related rates problems is that you take note of the variables that are involved in the problem, and then make sure that, I would even say step number one is you've got to write down some kind of an equation that involves the variables in question. And then you'll need to take the derivative of that equation. Probably with respect to time, although sometimes not, but usually yes. So the given I mentioned is dV dt, that was 100 cubic centimeters per second. The unknown is dr dt, and we want to find dr dt when r equals 25 centimeters, which is when the radius is equal to 50 centimeters. Here's the equation that we need in order to work through this problem. V equals 4/3 pi r cubed. And as I mentioned, we're going to take the derivative of that equation. So the derivative of v, can I get these on the screen at the same time? There we go. So the left-hand side just says v, and we're going to take the derivative of that with respect to time, which is going to equal, if we were taking the derivative with respect to x of x, the answer would be 1. Here, we're taking the derivative with respect to t, not v, but t. So we still take the derivative of v, which, much like taking the derivative of x, still turns into a 1, but then the chain rule says we have to multiply by the derivative of the inner function, which is v. And the derivative of v is, I have no idea what the derivative of v with respect to t is. So I always think of it like we're just writing down, look at the bottom of your screen there, it's almost like we're just writing down a little note that we took the derivative of v with respect to t. We don't know what it is in terms of t, but there it is, okay? On the right-hand side of the equation, I don't do this. On the right-hand side of the equation, we've got 4/3 pi r cubed. We're taking the derivative again with respect to time. So we still have to take the derivative of r cubed. The 3 still multiplies out front, multiplying into the 4/3. 3 times 4/3. The 3's cancel, leaving us just with a 4. We keep the pi. Pi is a constant value, so the 4/3 pi was all the coefficient. And it got multiplied by 3. The 3's canceled, we're left with 4 pi. At the bottom of your screen, you can see 4 pi. You also, at the bottom of your screen, see the r variable that's being squared. It was cubed. We subtracted 1. Now the exponent is a 2. Great. However, we're taking the derivative with respect to t, which means we need to use our chain rule and multiply by the derivative of the inner function. At the top of your screen, the inner function is r. Cubing is the outer function, but the inner function is r. And so the chain rule says at the bottom of your screen, we have to multiply by the derivative of that inner function with respect to t. I don't know what r is with respect to t, so I can't really take the derivative, so I write down dr dt, and that tells me that I did indeed take the derivative of that inner function, whatever that inner function is. So in this particular question, the unknown quantity is dr dt. Remember that this problem told us that the rate of change of the volume with respect to time was 100 cubic centimeters per second. So that's dv dt. I've already circled that here. And we were told that the diameter is 50 at this particular point in time that we're inspecting, which means that the radius is 25, so that r value needs to become a 25, which means the only thing that they didn't tell us was dr dt. Whether you plug your numbers into this equation first, if you plug those numbers into this equation first and then solve for dr dt, or if you do what Stewart did in his 8th edition calculus book here, he decided to isolate the dr dt first. And you can see on the right-hand side, the r variable is still there, and this unknown dv dt is still there. And then he goes on and plugs in his two values, the 25 and the 100, into the right-hand side of the equation. You see the 25 and the 100 there. He cleans this up, simplifies, and is left with 1/25 pi. That is the rate of change of the radius with respect to time. And that's all we were trying to figure out. The radius of the balloon is increasing at a rate of 1/25 pi, or approximately 0.0127 centimeters per second. And that's it. That's the whole concept. That's the whole process. It's my iPad freaking out. So again, the general idea of this is, at least the way that I do it, the first thing I do is read my question. The next thing I do is I write down an equation that models whatever's being described. In this case, it was the volume of a sphere. So I don't even read any further. I immediately write down the equation for the volume of a sphere. V equals 4/3 pi r cubed. And I know that it's a related rates problem. So maybe I finish reading the question, but then probably I'm taking the derivative with respect to time, making sure to use my implicit differentiation combined with the chain rule, because I'm going to end up with these weird things, dv dt, dr dt. So we need to make sure that those end up appearing, and then either solve for your unknown and plug in your given values, or plug in your given values and solve for your unknown. Everything that I just said, you should write down as a step-by-step procedure in order to solve these types of problems. and then see if you can indeed use that process. I'd be willing to bet it'll work 9 out of 10 times. Let's check out this 3.9 homework that I'm going to be assigning to my students. And let's just talk briefly about some of the equations that are going to be involved and make sure you've got everything you need in order to tackle these questions. Each side of a square is increasing at a rate of whatever. At what rate is the area? So we've got sides of a square and we've got area of a square. I'm not even reading any further. Area of a square, I have to turn on my pen. Area of a square is equal to x squared. I know that it's a rate problem, probably a related rates problem, because it says each side of a square is increasing at a rate of, which means I'm going to need to, and it's a rate of 6 centimeters per second. Per second means I've got time in the denominator, which means I'm taking the derivative with respect to time. So I haven't even read the rest of the question yet. I'm already going to take the derivative of both sides. Derivative of area with respect to time is equal to derivative, of the right-hand side. Take the exponent, multiply it out front, keep the variable, decrease the exponent by 1. So now it's 2x to the first power. Chain rule says I have to multiply by the derivative of the inner function. That's dx dt. Okay, now I'll read the rest of the question. At what rate is the area of the square increasing? At what rate is the area of the square increasing? Rate. Area of the square. That's dA dt. And this equation, very conveniently, is already solved for dA dt. When the area of the square is 49. Now, let's take it from the top. Each side of the square is increasing at a rate of 6 centimeters per second. In my problem, it says 6. This value is dx dt. It's the rate of change of the side length of the square. So I've got this covered. We want to know the rate at which the area of the square is increasing. So we're going to be figuring out dA dt, so I don't have to worry about that anymore. The other blank that I'm going to need to fill in is that x value. When the area of the square is 49 square centimeters, what's the side length of a square? When the area of the square is 49, it is 7. So this value over here, the 49, ends up translating to be a 7, which is going in for this x value. All right, so let's plug these things in. I don't know what dA dt is. On the right-hand side, though, I've got 2 times my side length is going to be 7 times the rate of change of the side length is going to be 6, which means that the rate of change of area with respect to time is equal to, however you want to do that, 6 times 7, 6 times 6, 36, 42, double 42, 84. And that's 84 square centimeters per second. So did it work? Did my strategy work? I wrote down an equation that describes the scenario. We were talking about the area of a square as defined by its side lengths. And then I didn't even finish reading the question. I knew that it was with respect to time because it said 6 centimeters per second, so I took the derivative with respect to time. And then I plugged in the given information. The 6 was very easy to plug in. The 49, I had to take the square root and plug that in as a 7 in for a side length. And then my unknown was already isolated, so it was plug in values and solve. So I did it in that order. Plug in values, solve. Let's see if it works in number 2. The length of a rectangle is increasing at a rate of whatever. Its width is increasing at a rate of whatever. When the length is blah and the width is blah, how fast is the area? of the rectangle. I already know, well, I had to read the whole question pretty much to find out that what we're really talking about, the relationship I'm talking about, is area. It could have been perimeter, so we did have to read the whole thing. It turns out that it's area of the rectangle. How do I find the area of a rectangle? A equals length times width. It's with respect to time because the rates that were given to us were centimeters per second. So we have to take the derivative with respect to time. That would be dA dt. That's how fast the area is changing with respect to time, is equal to, now the right-hand side of this equation is a product, L times W, length times width. So we have to use the product rule combined with our implicit differentiation. So I'm going to keep my first factor the same, which is how I usually do it, multiply by the derivative of the second factor. That's dw dt. Chain rule says plus derivative of the first factor, that's dl dt. Keep the second factor the same, that's w. And now I start plugging in unknowns. I don't really want to have to be shuffling these weird looking variables around. I'd rather put numbers in there first and then move numbers around. I don't want to divide both sides by dw dt if that's what I end up having to do. I'd rather plug in whatever dw dt is and divide both sides by 5. Wouldn't you rather divide by 5 than divide by dw dt? Yeah, me too. So let's plug in some numbers. Now, if I were on a regular piece of paper, I'd be going vertical with this thing. In fact, I'm going to. Can I? Let's see if I can do this. Can I get a white pen and make it enormous and just cover this up? So clever. Clever boy. There you go. Now I got some room to work. Okay. Do they tell us dA dt? No, because it wants to know how fast is the area of the rectangle increasing. So dA dt is what we're solving for. Do they give us a length? Yes, 15. Doesn't matter whether I plug in the length and the width or the width and the length. It does because of the multiplication that's happening here. I do need the actual given length to be multiplied by dw dt. So in this case, it matters. So the length that they give us is 15. The rate of change of the width that they gave us is 5 centimeters per second, plus dl dt is 8 times the width that they gave us was 13. So dA dt equals 50/75 plus 80 plus 24 is 104. Double check my arithmetic. I'm not very good with arithmetic. Is equal to 179. So when the rectangle is at a certain size and the two different side lengths are increasing at their respective rates of increase, the area of the rectangle will be increasing at this particular rate. Who cares? Why would anybody care about something like this? The balloon example is probably better because if I'm trying to get my balloon to increase its radius at a particular rate, I might need to be pumping air into the balloon and be changing its volume at a particular rate. And if I don't have a pump that's capable of pushing air into the balloon at a sufficient rate to get the radius to increase at the desired rate, then I might have to get a bigger pump. Why is that a better example? Does anybody ever need to be expanding a balloon at a particular rate? Probably. I don't know. Okay, so maybe it was a bad example. I'm imagining a commercial that I saw for a company that takes a cement slab and puts I think they put balloons underneath it or something, or foam or something, and they end up jacking these cement pads up after they've kind of sunk down into the ground in order to level out a patio or something. So you might need to be pushing volume in underneath that concrete slab at a certain rate in order to get the thing to raise the platform. All right, I'm reaching a little bit. What was this next problem that I wrote over the top of? Hopefully you wrote this down. I'm going to erase this stuff, and that way I can get access to that previous problem again. There it is. Yeah, that works. A cylindrical tank with a radius of this being filled with water. How fast is the height of the water increasing? So we've got a cylindrical tank. It's got a radius of 7. It's being filled with water at a rate of 2 cubic meters per minute. Cubic meters means we're talking about volume, which means I need a volume equation that relates to the radius of a cylindrical tank. So cylindrical tank. My dad would judge me. I shouldn't be drawing the back. You can't see that part. You shouldn't be drawing that part. So I've got this cylindrical tank. We could make it dashed back there. It's got a radius. We don't have to know what the height of the tank is. Apparently it's tall enough that it's accommodating however much water it is that we're putting into it. The volume of a cylinder is equal to base times height. I used a capital B for base because the base is actually the area of a circle. So in this case, this is equal to pi r squared h. And cylindrical tank, radius 7, filled with water at that rate. How fast is the height of the water increasing? So how fast is the height of the water increasing? That's our unknown. And the answer to how fast is going to be a rate, which is going to be dH dt. So you're going to need to take the derivative of v equals pi r squared h with respect to time. You're going to end up with a dv dt, a dr dt, and a dh dt. And remember, you're going to have to use the product rule over here. Factor the pi out of the derivative process, use the product rule, take the derivative of r squared h, and then distribute the pi in later, because the product rule is going to give you 2 terms. Multiply that pi in later. Or maybe don't. After you take the derivative, plug in your known values. Maybe you won't want to distribute the pi in there. You're going to have to play that as it goes. The radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing? So this is a volume of a sphere problem. Volume of a sphere equals 4/3 pi r cubed. They're giving you when the diameter is increasing, or rather when the diameter is 44 millimeters, 4/3 pi r cubed. That's radius. Convert that diameter to an r value. Plug that in as one of your known values. A snowball, sphere, you think, melts so that its surface area decreases at a rate of 5 square centimeters per minute. Find the rate at which the diameter decreases. Interesting, when the diameter is 9 centimeters. We need an equation that describes surface area of a ball. You could call it SA, I suppose, or just capital A, is equal to 4 pi r squared. You're going to be taking the derivative with respect to time because minutes are in the denominator. So you're going to have dA dt on the left-hand side. You're going to end up with a dr dt on the right-hand side and an r value on the right-hand side. You're being given the rate of change. You're being given the rate of change of the surface area. It's decreasing at a rate of 5 square centimeters per minute. Decreasing. So what are you going to put in for your dA dt value? Think about it for a second. dA dt the area is decreasing at a rate of 5 square centimeters per second. So dA dt is going to get replaced with what? It's going to be a -5. So don't let that throw you. If something's decreasing, you should assume that it has a negative rate of increase. Your R value is not given to you directly, but it's given to you indirectly because we're being asked about when the diameter is 9 centimeters. So you're going to have to convert that to an R value. And we want to find the rate at which the diameter decreases when the diameter is 9 centimeters. So we're looking for dd dt. You can bet that whatever dr dt ends up being is going to be half of your correct answer, because the diameter is twice the radius. So if dr dt ends up being -2, then your final answer is going to be -4. If dr dt ends up being -6, then your answer is going to be -12. For number 6, it gets a little bit more complicated, but I remember wrestling with this problem myself when I was in a Calc 1 class, and so I want you to tackle this one on your own. My recommendation is, though, that you start with a clean sheet of paper and draw yourself a really nice diagram. Get a ruler, get a triangle, okay? A piece of cardboard that actually has a right angle on it, so you can draw yourself a really nice diagram of the street lamp. You know, if you used a ruler, and if you have a ruler that has centimeters on it, the idea that the street light is at the top of a 15-foot tall pole, scale this diagram, make it 15 centimeters. This is actually an architectural scale. Where are centimeters? Actually, I don't think there are centimeters on this thing. It's all in portions of an inch. But anyway, you know, the scale that's on here, this is probably centimeters, actually. 15 centimeters is only like, you know, half the height of my head. I've got kind of a long head, but it might be nice to draw this diagram to scale. And then as part of your diagram, so this is street light. Let's draw a rough sketch. Ground, street lamp, 15 feet tall. Here's my lamp. There's a man who's 6 feet tall. He's walking away from the pole with a certain speed. How fast is the tip of his shadow moving when he's 30 feet away from the pole? So if that pole is 15 feet tall and he's 30 feet away, I gotta make him like twice as far away as the pole is tall. And so here's our man. And he's 6 feet tall. Yeah, that might actually be pretty close to about 1/3 of the height of that pole. Right, so with a scale, you could be drawing him at exactly the right height. This is 30. And his height is 6. Streetlight is mounted 15, man 6 feet tall. Pole. He's walking this way at 5 feet per second. Straight path, how fast? The tip of his shadow. So this light is shining telling you, digital pen, so nice that I can just grab a different colored highlighter and change the opacity of it, and it's so much fun. So here's his shadow on the ground. Could you figure out how long his shadow is? The answer is yes. And the relationship that you might consider designing would involve the fact that at the moment you don't actually know the length of his shadow. So I would call that x. So you have a shadow with length x and a man with a height of 6. And then you have this total distance away from your light pole. 30 plus x is the total distance of the tip of the shadow away from your light pole. And the height of the light pole is 15. So you have a horizontal distance of x and a horizontal distance of x plus 30. You have a height of 6 and you have a height of 15. Maybe some kind of a proportion would be a good idea to set up. Something over something equals something over something. And when you have a fraction equals a fraction, are you allowed to cross multiply? Is that the only time you're allowed to cross multiply? Yes, it's the only time. You're just multiplying both sides of the equation by both of the denominators. That's what's really happening. What you do to one side, you must do to the other. What is it that's changing at 5 feet per second? A man is 6 feet tall, walks away from the pole with a speed of 5 feet per second. So that number 30 is actually changing at 5 feet per second. Interesting. So maybe that distance, so that you can take the derivative of it and turn it into a rate, like dA dt or dV dt, something like that, because you're going to need somewhere to take that 5 and plug it in. At least in my example, it's a 5. So maybe the 30 should originally be represented as a variable, so that then when you take the derivative of it with respect to time, it will become d variable dt, and then you can plug in the 5 there. I wonder what that's going to do to that x. How fast is the tip of his shadow moving when he's 30 feet away from the pole? Not only is the length of that shadow growing, but the fact that the man is moving, he's pushing the tip of his shadow as his shadow is growing. So it's almost like you have two horizontal values that are changing, and in this case moving to the left at the same time. You've got your work cut out for you on this one. This is going to require some creativity. Don't just Google how to do this problem. Do all the rest of the problems around it. I'm telling you, the satisfaction you're going to get from figuring this one out on your own will be very nice, okay? I'm not going to say any more about this one, but please try it, wrestle with it for a while. You've got like multiple days until this homework assignment is due, so see what you can do with that one. Two cars start moving from the same point. One is traveling south. One's traveling west at different rates of speed. At what rate is the distance between the cars increasing 3 hours later? At this rate of speed, how far has this car traveled after 3 hours? At this rate of speed, how far has this car traveled? You've got two distances, and you have the rates of change of those distances. And we want to know the distance between the cars. Wow, if one's going south and one's going west, I feel like this is probably a right angle. And the distance between the two cars looks a lot like a hypotenuse of a right triangle, doesn't it? So remember, you need to design an equation that describes this scenario. And this scenario, visually at least, looks to me to be the relationship between the side lengths of a right triangle. Maybe that'll help you on that one, since I only helped you a little on the previous one. And number 8, gravel's being dumped from a conveyor belt at a rate of this many cubic feet per minute. And its coarseness, there must be a technical word for that, is such that, such nice grammar, is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. So diameter of the base of the cone and the height of the cone are the same. How fast is the height of the pile increasing when the pile is 7 feet high? Well, I can tell you first, if the height of the pile is 7, then the diameter of the base of the pile is 7. I know that much. It's pretty good, right? And we know that, Look at this number right here. The gravel is being dumped from a conveyor belt at a rate of, now that says 20 cubic feet per minute. You need to know that if it's cubic feet or cubic inches or cubic centimeters, that we're talking about volume. So you're being given a dV dt value, which means that the equation that you design better have a V in it, where V stands for volume. And that's going to be the volume of what, do you think? It's that cone right down there. I can see it from here. What's the volume? What's the equation that describes the volume of a cone? It's 1/3 base times height. Notice the capital B again. The base of this thing is a circle, so this is going to be 1/3 pi r squared times h. You're going to need to take the derivative of v equals 1/3 pi r squared h. Remember that the 1/3 pi makes a constant. 1/3 pi, that's like a coefficient. So factor that out of the derivative process. Take the derivative of r squared h. Use the product rule and the chain rule and your implicit differentiation. On the left-hand side of the equation, you're going to have a dv dt. On the right-hand side, you're going to have 1/3 pi times the quantity. And inside those parentheses will be the results of your product rule. And the results of your product rule better contain a dr dt and a dh dt. They gave us dv dt. I've already circled it in the problem. How fast is the height of the pile increasing? So we're looking for dh dt when the pile is 7 feet high. So they're giving us h. Since they gave us h, does that mean they're also giving us r? Sort of. They gave us h, which means they're giving us also the diameter of the base of the pile. So sort of they're giving us r. You'll have to figure out what r is from the diameter. And what else are they not giving us? They're asking us, let's see. There's going to be a dv dt on the left-hand side. And on the right-hand side, there's going to be an r and a dr dt and an h and a dh dt. So they gave us dv dt. I circled that up here already. They gave us the, how fast is the height of the pile increasing when the pile is 7 feet high. So 7, that's the h value. So they gave us this. They gave us this. Since they gave us h, they sort of gave us the r value. We can figure out the r value from the h value. And they're asking us how fast is the height of the pile increasing. So this is the unknown. This is what we're trying to figure out. But they didn't give us dr dt. Interesting. What in the world are we going to do about that? Well, I know what to do about it. And they how do I describe this? They didn't give us dr dt, but they gave us h, and h and r are related. I think what you should try to do, I know what you should do, is instead of using the variable r, which is causing you here to have a dr dt that you don't know what it is, try replacing r in this original equation. Try replacing r in that original equation with something that has to do with h. Since we know that there's a relationship between r, which is the radius, d, the diameter, and h, which is the height, see if you can replace r with something that has to do with h. Then the entire right-hand side of your equation is going to be in terms of h. And not only will you not have an r anymore, but you won't have a dr dt anymore. You'll just have h's on the right-hand side. And when you figure that out, I think you'll also be pretty proud of yourself. You'll take the derivative, you'll still have an h, you'll still have a dh dt, but they gave us dv dt, they gave us h, the only thing you'll have to solve for is dh dt. And that is it. The field has gone white, which means that's my flag of surrender, I suppose, as far as this chapter is concerned. Whew, that was a lot of fun. Thanks for hanging with me for this chapter. I appreciate it. See you in the next one.